Good morning, everybody. So let's start our second day. First of all, I would like to thank the organizers, Manfred, Ernst, for doing this symposium in a classical form. When you see the people, when you can talk to them. Last year, I participated to 2 conferences online, and I just didn't like it. So it's a very good format, classic, but probably the best. So when Manfred asked me about the title of my talk a few months ago, I didn't know what to answer in the beginning, because last time at the first symposium I presented 2 talks, one on B stars, one on B-bracketed stars. But since we have an observatory and we always take new data, we always analyze them, so there are some new results, and I decided to kind of give a broader talk on a number of binary stars. Some decades ago, I looked at the sky once and fell in love for the entire life. Just probably some people came to the observatory, saw the stars, but even a glance with no telescope, just naked eye, can make it. And at that time, I didn't know what a professional astronomer was. I just was fascinated by stars. Orion was my best constellation. I would go out of my house and with a theater-like binocular look at Orion and picture those stars. And with the time, I tried several different research areas and finally got stuck on emission line stars. But in addition to those emission line stars, I'm going to talk about some normal stars which do not interact, which do not have any circumstellar material, or at least the amount of that material is not enough to be detected in the form of either infrared excess or emission lines. And binaries are always interesting and different. Sometimes you cannot predict what you get when you start observing an object. So I will start with some introduction of my closest collaborators. There are more, of course. At our observatory, which I will show in the beginning before presenting the results, we have 3 observers. Professor Danford is a retired astronomer who designed our observatory back in the 1970s, and he retired about 8 years ago, but is still an active observer with our spectrograph. And then recently we got a newer, younger astronomer, Alicia Arnio, who studies mostly young stars, but also is involved with our observatory. And then I have 2 people, Sergei Zharikov from Mexico and Nadine Mansei from CFHT telescope, who try to help in any ways, because those B-bracketed stars are not recognized to be a hot topic. And it's really hard to get time on bigger telescopes. So Sergei has a 2-meter telescope at the observatory San Pedro Martir in Baja California, and Nadine is a project science on Espadon's spectropolarimeter at the 3.6-meter CFHT. Then I have a cohort of young astronomers who do their PhD projects with me, and with them we recently discovered a few new binaries among the B-bracketed stars. And finally, as a professor at the University of North Carolina, Greensboro, I teach introductory astronomy courses. And at our university, you don't have any astronomy program who prepare professional astronomers. We only have physics. And sometimes students, they look at see our telescope and decide to try some research project. And there are 3 names of my recent students. One of them came to me when he was at high school about 2 years ago. Now he is an astronomy student at university in the state of Tennessee. All right, and there are more. So just a little bit about our observatory. This is an aerial picture of it, which was taken by a pilot of a small plane. in 2010. Somehow people from our department found him and he shared his picture. So that was 2010. You see lots of trees. This is a Google image from 2021. So the area around the observatory has less trees, and because of that we have better access to southern stars. So this is our latitude, so we can go down to about minus 35 degrees. So the telescope is 81 centimeter. So 81 is kind of strange, but in the old imperial system is 32 inches, so which is probably more standard. It's f to 13.6, so we have to use a focal reducer to connect to our shell spectrograph, which we bought in 2011. And since that time, we've been observing it every clear night. Until 2019, the observatory was not automated, and it was run on old IBM PC 486 computers. But fortunately, we found a company called Sidereal Technology who changed our navigation system, and in 2019, they automated the observatory. So this spectrograph gives that spectral range with this moderate resolution. And I'm the only one who reduces the spectra, and until now we have over 10,000 spectra, which are combined spectra from individual exposures. So here is a recent picture of our telescope. So you see some automated covers, which sometimes fail, by the way, because it was a problem to balance them. So you can see some counterweights here. And this lid is composed of two pieces. You can raise two pieces at once, or you can connect them together with a special mechanism and can raise both up. Okay, so this we have a set of surveillance cameras which look at the telescope from different angles, and one of them looks at that mechanism which connects the two parts of the slit of the observatory. One computer is dedicated to collecting data, and the other one is connected to the telescope and the weather station. And in many cases, we see on our weather station that there is rain while stars are bright and there seems to be no cloud. And we figured that probably there are lots of bugs which bombard that piece of which reduces the data on humidity, temperature, and conditions. Anyway, a few months ago, somebody broke into the observatory. So they just destroyed the lock, came in, and took nothing. So it was so strange. And since that time, we added some more cameras to look around the observatory, just in case we need to call the police. Because it's very remote. There are a few houses around, but mostly animals. Okay, so now let's get to the scientific part. Science evolves, and probably at some point we thought that all stars were spherical. They're mostly lonely stars. You can spot just a few stars with the naked eye. Like, for example, that Mizar or Mizar, how should I pronounce it? Because in Americans say Mizar, but probably Mizar is the proper pronunciation. Anyway, with time, and that's what we heard yesterday, it turned out that many stars, especially very massive stars, are mostly binaries. Of course, many are not interacting binaries, but interaction between the components makes our life maybe a little harder, because if you do not resolve the components, then the brightness is off, and you can get luminosity off, and maybe Gaia, which is measuring parallaxes, may also get confused. And we can see that that photometric, spectroscopic, kinematical distances on some objects, especially far away from us at a few kiloparsecs, these distances are not consistent with what Gaia shows. But on many stars, especially within the nearest kiloparsec, this coincidence is very good. So, with the binary star, with the binary system, which are connected by gravity, we can use the old Newton's law of gravitation and directly determine stellar masses, which we know determine the entire evolution of a star. But if the binary is initially closed, then exchange of masses can occur, as I will show in the example of some objects, and the lives of these stars change. Again, if we know contributions of the components, we can correct the brightnesses and then the luminosities, and eventually, after we get a lot of material for many star binary systems of many kinds, we can verify and improve the models of stellar evolution. So my main project is in the bracketed stars, and some time ago I defined a subgroup of this kind of objects, and with my collaborators we study them now one by one, and in recent years we discovered quite a number of new binary stars, or at least determined fundamental parameters of them. So that will be in the end. Since I came to the United States, my first job was at the University of Toledo with John and Karen Bjorkman, who studied VE stars for a long time, and then I also fell in love with VE binaries. Initially with VE stars, but it turns out that many, if not all of them, are in binary systems. So I will show a few results on this recently found or suspected binaries, except for Delta Scorpii, which came into focus in the year 2000, when it was started developing a disk of gas around one of the components. But I will start with normal stars, because there are many bright stars which were observed I don't know, maybe 50, 60 years ago, maybe even a century ago on photographic plates. The orbits were measured, but they were not constrained very well. And the science works just like that. So if you do not study something which has not been studied at all, then you pick an object or some result which was already produced by some scientist maybe a few decades, maybe even centuries ago, and you do the same project with better equipment, with high accuracy, and when we know everything more precisely, then our knowledge about tiny, maybe details of stellar lives and evolution also improve. Okay, we observe most of the stars, and even this one, which is a 10th magnitude star, at our observatory. 10th magnitude is our limit, but if you take an exposure of 2 hours or 3 hours, then you can get a good spectrum of with emission lines, not absorption lines. And all these stars are pretty bright. First magnitude, fourth magnitude. It just takes maybe 10 to 20 minutes to get a decent spectrum in a series of exposures. So we use our observatory a lot. Okay, so let's start with individual objects. So MITES-R B, it's a famous binary, so you can resolve MITES-R null core if you have a perfect vision. As I usually tell my students, no clouds in the sky, no light pollution, then you probably can see those stars separately. And as far as I know, it was a criterion to select soldiers into the Roman army back centuries ago, if you can resolve them. But in reality, this pair is actually a system of 6 stars. So that bright one With the naked eye, you see those 4 stars together, and our core on its own is a binary. So we observed MITES-R A for a long time, but then I looked at SYMBAD and saw that MITES-R B was observed last time with kind of numerous spectra 50 years ago, more than 50 years ago. And the solution, the radial velocity curve, was not perfect, although the period was defined. So you can definitely see that in this picture. So this is the historical observations. Unless I missed something, I didn't see any newer study of this system. So it was done in 1965. And we decided to get some more spectra. We did that since 2015 to 2022. I didn't include the latest results, and this is our radial velocity curve. There is a little scatter of points here because at some point our shell, something changed with it, and we lost the best transmission. And I had to send the spectrograph back to France, to François Cochard, who repaired it. And actually, it's now better, because it looks like that position of the hole for the fiber should be established very precisely. And something happened and it moved. So for a period of time, we got out of focus. We were registering only about a quarter of the light we did before. But it took him a month to repair that, and now we are back in business. Anyway, you look at the scatter of points for this old photographic data, and the accuracy, I mean, if you average them, is about maybe plus minus 3-4 kilometers per second. In our case, the internal precision is about 300 meters per second. And when we correct for this scatter, we always observe a radial velocity standard, maybe 2, sometimes even 3 a night. We can make it like this. So it will be much better defined compared to this curve. And let's see what we can get out of the radial velocity curve in the period. So there is semi-amplitude of the component whose lines shifting back and forth, and you have the orbital period. If the radial velocity curve is distorted, is not sinusoidal, then it means that there is eccentricity in that orbit, and in this case it was found to be pretty large eccentricity. So eccentricity should also go here, and this is the observed part of the mass function. And to the mass function, the theoretical side of it is a combination of the inclination angle of the rotational axis of the system to the line of sight and the masses. If you assume the masses and some angle, you can actually calculate those curves, which are dependencies of mass of one star by the mass of the other star in the system, given the angle, the tilt angle of the system. And for the main component of MITES-R B, this is kind of a conservative estimate of the mass of the brighter star. And I don't think the tilt is very big. I mean, we don't look at that system about face on, so probably the angle is more like 30, 40, 50 degrees. And here you can read the range of masses for the secondary component, which is somehow pretty low mass star. Yet we don't see its contribution to the spectrum because it's that low mass and it's that faint. Anyway, so we improved. I didn't give precisions on that, so it's still work in progress. But at least the period changed a little bit, and the eccentricity changed with our more precise data. So we will continue working on that object. And then the second star, which we picked up, was second Lacerta. Again, bright star, 8523. It's a double line binary. MITES-R B was single line binary. and you can see that in some spectra the lines are split. And it turns out that there was some attention to this binary, but long ago the largest set of data was produced in the beginning of the 20th century. And here are the parameters. You see that the period is pretty small, just 2.6 days. But people kept trying to improve their orbit. The solutions look very similar, but the semi-amplitudes of the Radial velocity curve are a little different, and within 3 sigma they're about the same. Again, I don't have the final precisions for our data, but they are about 1 kilometer per second. What we don't know about this system is precise spectral types or masses of the stars. With the previous solutions, the masses were all over the place. 7 solar masses, 6 solar masses. We came to this set of masses, 5.2 for the primary, 4.3 for the secondary. And here is a comparison of the data from data taken in 1908. The paper was published in 1910. So you see that it's about the sinusoidal curve, but there are some distortions around that sinusoid. And our data, although the number of data points is still less than was a century ago, but the sinusoidal curve is a lot better defined compared to all these wiggles around the main sinusoid. For the secondary star, it's less constrained, but we will figure out maybe there are some systematic errors. What I also was puzzled about, if you do a Fourier analysis of the data, in all sets of data, you have 2 sets of big peaks. So this is a peak for 2.6 days, and there is another peak for 1.6 day. And I have a suspicion that it may be a triple system, because sometimes the line profiles look split. And there is no companion. Sorry. So there is no another companion, another peak companion on the other side. So you have a comment on that?
I would say it's a daily alias.
Well, we still need to explore it. But I know that there should be aliases, but I think there should be another alias on the longer period.
Not necessarily.
Okay.
You need to look at the spectral window.
Mm-hmm.
I don't know which technique you use to do the Fourier periodogram, but if you use the technique which is a modified Fourier, because it's not an even sample, right? Then you can calculate the spectral window, and then you will see if you would expect both peak or only one.
So it may be connected to the cadence of observation.
To me, it's totally
maybe not real.
Yeah.
But again, so some lines look kind of more than split into 2 parts. So we will keep. Yeah.
Did you try disentangling?
We are working on that. So, but in any case, it's an improvement from old photographic data with everything. So they typically don't show the a typical error bar, but it's much larger than what we got. This data, we cannot do a good cross correlation because these are hot stars and there are not many lines. So we measured a few lines individually and then average the results. And when we do a mass function, we can do that for both stars. And the ratio of the amplitudes of the Radial velocity is about this one, and it coincides with the field angle of 30 degrees, which was already predicted about a century ago. But for some reason, those great people like Lewton and his collaborators, Otto Struve and some other famous American astronomer, I don't know, they used Fourier analysis at that time. But they didn't go I mean, they didn't do that step, determining the mass function and the tilt angle. All right, so this kind of summarizes my examples of normal stars. Again, good projects for people who have even a iris-free or shell spectrograph, and that's a good training project for students. Now, the next part, let me just keep track of time, is about classical B stars, which the first one is Gamma Cas, and is going to talk about this kind of stars. Turns out it's not just a single star, but it's a prototype of an entire group. They were discovered back in the mid of the 19th century, visual spectroscopy, and these are typically fast rotating stars with a rotation rate of about 70 to 80% of the breakup velocity. And they are all close to the main sequence, so they probably mostly near the end of the main sequence evolution, but we find some of them in young clusters. And they all have disk-like envelopes. Still, there are debates of how they are produced. So it looks like it's a combination of non-radial pulsations and fast rotation. But since about 45 years ago, there were ideas that the main star in the, if it's a binary, the main star was spun up by a companion, by mass transfer, and that was the first hypothesis which was proposed by Peter Harmanets. I think at that time he was his supervisor, so Luke Kujish. They thought that these stars are in an ongoing mass transfer, but we astronomers didn't find any confirmation to that, and this idea was rejected for about 2 decades. People thought that most of these stars are single stars. But as we get more and more observations, especially with the help of lots of amateur astronomers whose observations are accumulated in the BESS database in France, it was possible to find a lot more binaries. And among 24 brightest B stars, I think 14 now have been recognized as binaries, so more than 50% binary fraction. And I believe that we don't know that others are binaries just because there is not enough observational material or there was no analysis. Now here you can see the some clues to formation of the line profiles. If the disk we see a face on, then there is no Doppler shifts for the material which moves towards us and away from us, and there is no split in the emission line profile. But if the tilt changes, we see different central depressions between the peaks, one of which is forming in the material which moves towards us. The blue shifted one and the red shifted one is formed in the material which moves away from us. But it's a simple picture because there is a number of stars which are observed about 45 degrees, the tilt of 45 degrees, but they do not have double peak profile because especially in the H alpha line, the optical depth is big, and some additional kinematics of the disk, or maybe some additional parts of the envelope, they create a central peak which actually veils, which gets on top of that double peak structure, and it can only be revealed when the V stars loses its disk, the amount of material in the disk decreases, and then you can see a double peak profile. So how do we discover those binaries? One of the methods is obvious. Just like in normal stars, we try to look for the shifts of the spectral lines, absorption lines, and for the bisector velocity of, for example, the H alpha line. but the absorption lines are very broad because of fast rotation of stars. And these are B-type stars. Again, there are not many lines in the optical spectra. So we may want to find some other methods. Of course, for the closest stars, you can use interferometry of different kinds, but sometimes they're too close. And there seems to be another method which works in some cases. This method is searching for periodical variations of the peak ratios in double peak profiles. Of course, the H-alpha line is the best candidate because it's the strongest line. In spectra of many B stars, even the H-beta line is too weak, and it's hard to get its peaks because you need to have a model of the underlying star in order to remove the absorption parts. But it was shown for a few stars that the variations, so V over R, violet peak over red peak intensity, they are phase locked with the variations with the orbital period. And that's what we did for Aquarii, a binary system which was recognized around the year 2000. With the help of the MSHA community, especially with the help of Ernst, we accumulate lots of observations, and these are the V over R folded to the period of 84 days, so that's the period of this binary. And then we did a tomography, and so my colleague Sergei Zharikov is doing that, and we determined that in the disk there is an enhancement, so this is a density enhancement, which moves in sync with the secondary companion, which is much fainter in this system. The brightness ratio difference, magnitude difference, about 2 to 4. I think in this case it's 4 magnitudes, so we don't see any contribution from the secondary. So that was a good exercise, and we started to look at some other stars. And that second star, I think I showed that at the previous conference, Nu Geminorum. Also a bright B star, 4th magnitude. This is the radial velocity curve because its projected rotational velocity is just 150, 130 kilometers a second, and you can find a good range of the good wavelength range of the spectrum in order to have enough lines for cross correlation. So this is the radial velocity curve for which we derived from our data. At our observatory, we got about 300 spectra of this star. But at the same time, it has double peak profile, and we did the intensity ratios. And it turns out that the period is the same. I think the period is here. And it coincided with the period found in some previous papers. But even in the recent paper, people were not sure that this star produces phase log variations of the emission peaks. So now it's well established, and we're gonna do a follow-up publication on that star. Now a few more. I think I will show 3 more V stars. These are new ones. Last year I spotted this star, which was found to be a binary using HST and IUE ultraviolet observations spectra. The brighter component is a B-type star, so early B-type star with this temperature. Secondary is a subdwarf O-type star, and all this information was derived using the ultraviolet data. They had only 7 spectra, and on the basis of these 7 spectra, they determined that preliminary period. I am still puzzled with this accuracy of 0.01 days. But this year, an interferometry paper was published based on 4 interferometric positions of the secondary, so it's resolved, and the period turned out to be different. We started observing it last year, got about 40 spectra, and calculated the VOR intensity variation. And this is our period. It's very close to the interferometry period. So when you do Fourier analysis, and we use that internet-based service for exoplanets, that's just kind of quick and dirty tool. Of course, there are some other programs. So this is the Fourier spectrum with the biggest period on 63 days. Then if you fold the radial velocity, not the radial velocity, but the intensity ratio variations, it shows you some kind of a scattered phase curve, but it's in agreement with other methods. So it works in this case too. And I think the larger the mass ratio, the weaker the gravitational effects, and the smaller the changes in the intensity can be produced in such binary systems. So we turn to another bright star, which is of 4.7 magnitude, but it didn't get much attention, like, for example, Pi Aquarii. Pi Aquarii is located a few degrees away from that star, but it lost its disk, and that's what kind of attracted attention. This one was stable for decades with about the same strength of the emission line. So this was gathered from different literature sources. So there is a good distance now. And we decided to do some monitoring. So you see here the H-alpha line profile, and the red and black spectra show differences between the intensities and of the peaks, and they're very, very small. And when we collected all the data, it turned out that there are some changes in the equivalent of the H-alpha over the years. So for 10 years, it was declining. We have not analyzed the most recent data. It just came above the horizon during night time, so we can continue observations. But we collected data from BESS. There was a set of data taken by people from University of Michigan, and there was some historical literature data. And so it looks like it may be kind of cyclic, and that's another effect which you may want to study more closely. It may lose its disk, but I don't know, it was stable for so long time that no big changes, that maybe it will stay and recover, and in some years to come, we will see again stronger H-alpha line. The change is not very big, but in any case, it happens. When we calculate the intensity ratio, we still get a, well, it's not that decent peak in the Fourier transform, but it's here. And when we fold our data with this period, which is 72 days, it's very scattered. So you may not even trust that this is the period. But if you compare that to this, it's about the same picture. So that biggest peak, there is that scatter. So I just think that in Omicron Aquarii, there is a secondary component which is simply less massive compared to the main star. And here we didn't take care of adjusting the data from different seasons. We just plotted everything on the same graph. But maybe from orbital period to orbital period, there are changes in the intensity ratio. So we will do that. Last season we observed that star as frequently as possible, and for this season we are aiming at the same thing. So another suspected binary, but in the most recent interferometric paper, it was regarded as mostly confidently single star. So we will see. And finally, not for the talk, but hopefully I still have some time, this another love of mine, Delta Scorpii. It was recognized to be a binary in the beginning of the 20th century. from lunar occultation. So I don't remember the name of the astronomer, he visually saw that secondary component when the moon occulted the star. And then with interferometry it was resolved. It was shown to be a very eccentric binary, and the interferometrists, they warned people, observe the periastron at the year 2000, but he didn't care for some reason. And it turned out that in the year 2000, somebody spotted a slight, I think it was Sebastian Otero from Argentina, yeah, sure. He spotted a 3% increase in brightness. And Juan Fabregat from Spain took a spectrum and saw an emission line. This star was a standard of spectral classification. No emission lines for the entire 20th century, maybe even earlier than that. But it started developing a disk, and at the University of Toledo, where I worked at that time, we decided to take a series of spectra, although it's a very sudden object, minus 20, almost 23 degrees declination, and for Toledo it was about at the horizon. So we constrained the periastron and been observing that this star for a long time. So because of that big eccentricity, the separation between the components changes a lot. In 2000, it was not possible to resolve the components with interferometry near periastron, but nowadays it's possible. And this, what interferometry predicted, so these two curves, not solid curve, these were predictions from interferometry before we started spectroscopic observations. And we got about 20 spectroscopic observations, and we perfectly nailed the periastron, and this was a refinement for the periastron time and also for the properties of the entire system. But the period is about 11 years, so we had to wait until 2011, and in 2011 we got together with a group of amateurs, applied for time at Tenerife, and did 10 nights there. All nights are clear, and we observed that in 2011. So this is the H-alpha line profile, which looked like in 2011, and this is 2022. So we constrained the orbital period, so this is it's in days, here it is in years, and predicted that the next periastron should have occurred in April this year. So I sort of announced the campaign, and Yael and Gregor responded, and we got a number of spectra with the telescope. It's a telescope. Yeah, it's not just a spectrograph. So I understand. Yeah. Then we got some spectra from Ars group, from Ernst, and I was very lucky at our observatory. Since April 9th to May 20th, we got almost every night clear for observations of this star. So it's a first magnitude star, and because of that, even if it looks totally cloudy, you can still get a good spectrum. So this is the radial velocity curve, and in all these three periastrons, the source of the radial velocity curve was different, because in 2000 we observed only the H-alpha region and a few other lines, but the spectrograph at the University of Toledo at that time was able to cover very narrow regions centered on some astrophysically interesting lines, but the main one was H-alpha. And the solid line here is our first radial velocity curve. Then in 2013 we got a lot more spectra, again many in the H-alpha line, but it also has a very nice isolated line of helium-2 at 4686, and these are this dashed line, and the data points are from the radial velocity of the helium line. And they are not the same. And there was a suggestion that maybe it's a triple system. It was suggested by some theorists who study triple systems. So we just needed to keep observing it and trying to detect any deviations from the binary orbit close to apastron and probably periastron. I didn't have time to reduce all the data from this period because it's still ongoing. So these 2 points are from May 20th. And we still need to go about another month in order to cover the entire kind of big change in the radial velocity. But this curve comes from a cross-correlation. At that time, we just didn't have enough material for cross-correlation in 2011. And all sources may be different because H-alpha probes the circumstellar disk, helium line probes the atmosphere of the main star, but this also is supposed to give you an idea about the primary star. By the way, this red thing is the constraint for the periastron time. So it looks like it was a good prediction, but I still need to reduce the data here to constrain it better and try analysis of all 3 possible sources, the H-alpha bisector velocity and the 4686 line alone, and then when we combine everything, we will get it. We will get a better idea of what happened to delta scope in this periastron. All right, so I come to the last part, and yeah, there is still 15 minutes. About the BE phenomenon. So we started from normal stars which don't interact. Then in these stars, probably there has been or there is some mechanism which allows the material to get out of the star, fast rotation, non-radial pulsations, maybe a magnetic field, something else. And the B-bracket phenomenon, which was defined in the 1960s, is about also B-type stars, emission line, but in addition to a rich spectrum of permitted lines like hydrogen, like iron. Sometimes these stars are called iron stars because they have so much iron in emission. They also have forbidden lines, and forbidden lines form in a region with much lower density. For example, B stars, they seem to have smaller disks and higher density disks, and they don't show forbidden lines. And B stars show some infrared excess, which is due to free and bound-free radiation from hydrogen gas mostly. But in the regular stars, the infrared excess is much stronger. At the time of detection, there were no long wavelength detectors for infrared radiation, and that's why they picked up only near-infrared excess, but it cannot be explained by radiation from circumstellar gas. So it should be dust there. So combining this observational features, the forbidden lines and infrared excess, we can say that those envelopes, maybe not necessarily only disks, should be much larger than the B stars. But it turned out that the B-bracket stars, they contain, they have members from very different groups of different masses and different evolutionary stages. And probably because of that, the attention to this newly discovered phenomenon at that time was kind of partially lost. So one of the discoverers, Jean-Pierre Swings, took an administrative position at Liège, and as he told me, he would have done science, but unfortunately he was not able to do that. After about a decade, his group kind of wandered around. So we picked it up in the 90s. It turned out that half of the group was not classified because the luminosity was uncertain, or those objects showed features of other groups. So in the end of 90s, it was not clear what about 30 objects of that initial group observed. We finally kind of moved them in a separate group, found more members of that group, and called this group FS Canis Majoris objects. This is a variable star, about 7th, 8th magnitude, which was suggested by Jean-Pierre to be the prototype of the entire phenomenon. Turned out to be not that easy classified ones. Some features. The hottest stars, they have very, very strong emission lines. So these are all of iron lines, some forbidden iron. So this is the H-beta line. I don't know why some symbols didn't show up. And you see some strange line profiles. Others look like normal stars. So this part of the spectrum of this object is similar to Vega, for example. But this part doesn't show the emission lines, which also exist. And then in the infrared excess, there is a lot of radiation from circumstellar dust. So this is what the spectral energy distribution would look like if there would no material around the star. So circumstellar dust absorbs some radiation from the star in the ultraviolet, and the dust gets warm, and it emits radiation as a black body in the infrared. So it's an energy transfer from ultraviolet to the infrared, and sometimes the amount of radiation in the infrared excess is larger than the amount of radiation emitted by the star. And it may mean that either it's a binary or there is lots of attenuation of the brightness of the star by the circumstellar envelope, which include gas and dust. So there are a few examples of different spectral energy distributions. And that's kind of a sketch model which we came up with. I just modified someone picture, and that red star, which is not necessarily a red star. It may be a black hole. It may be a kind of very hot dwarf. But in any case, it's a binary system. The brighter the primary, maybe it's actually secondary, is a B-type star surrounded by a gaseous disk, and the entire system is surrounded by a dusty disk. If you look at the Kirby-Russell diagram for the brightest components, they are located here, and an immediate conclusion how such a low mass star, and you see the initial masses of stars here, these are models of stellar evolution for these masses in solar mass. Single stars of this range of mass cannot produce such strong stellar winds to account for the circumstellar envelope. So the suggestion is that they should be binaries. In some cases, we found secondary components. Two examples shown here. These are the fainter, but still visible in the spectra, cold stars. And in the recent years, we kept discovering new binary stars. So this one was from 2015, the 10th magnitude star in Taurus. You can see that it has some absorption lines which cannot be accounted by that B-type star. For comparison, a G8 type giant is shown with the lithium line, with the calcium line. We disentangled the contributions of the hot component and cool component, and here you see the positions of the hot companion and the cool companion along with the evolutionary tracks of interacting binaries. So that red track shows the initially more massive star, which finishes its evolution at the main sequence. Then it grows in size. Here it overfills its Roche loop, and the transfer of mass starts from this star to that star whose track is shown in blue. It was a lower mass star, about 2 solar masses, and it was still sitting at the main sequence when this star evolved off of main sequence. Now it started gaining mass, accelerates its evolution, and this is its predicted evolutionary path in the future. Now it's here, and the formerly more massive star is now a less massive star, and we caught it in this position, being a cool giant. So that's one possibility. Another possibility is this star. Again, we found it in a catalog of infrared observations. Turned out that it had a pretty large infrared excess. Its optical spectrum is not that of a dwarf, but it's more or less like a fainter supergiant, but still large star with something. We did this radial velocity curve and determined the period, 130 days, and found the mass function. So this is the mass function. Q is the ratio of the masses of the companions, and it's 1.7 solar mass, which is the minimum mass of the secondary component if the orbital viewing angle is 90 degrees. But if it's different and the mass of the secondary is somehow comparable with the mass of the primary, the estimate of the mass of the secondary increases. And we found that you can actually explain these observations only if the mass of the secondary is about 7 solar masses, and we don't see any trace of it. So our suggestion is that it's a black hole. These are just examples. And the third example is that starts for Puppies, which was classified as a normal supergiant, but it has some little H-alpha line. Even 7 years ago, the period was known, but the amplitude of the radial velocity curve was not constrained. Again, we did about 100 observations at our observatory. It's a very sudden star, minus 29 degrees in declination, but we constrained it's very good, so radial velocity. And finally found the mass function, and Danny van Beveren from Brussels helped us to calculate the evolutionary tracks for the initially more massive star and initially a less massive star. And we caught the initially less massive star is more massive star, so it used to be 3.6 solar mass, now it's 8.8 solar mass. But the initially more massive star lost about 5 solar masses, mostly onto the primary, but some spilled over and formed a little envelope. And now this star is supposed to be here. So its temperature is about 50 or 40,000 degrees. And there has not been ultraviolet observations to see any contribution from this now secondary one. You can only spot the contribution if you observe it at wavelengths lower than 1,000 angstroms. So it needs to be kind of soft X-rays or far ultraviolet. And this is another example. Again, that group of Fs Canis Majoris stars may be caught at different evolutionary stages of transmission. So this is the lowest mass member. If you look at the optical spectrum, it looks like an early A-type star. And for comparison, I put a spectrum of famous planetary nebula, red rectangle, which is shown here. And our star doesn't show any sign of the envelope, although it's located closer than the red rectangle. So first suggestion is that it is about the same thing. And the infrared excess, again, is shown for our star and for red rectangle. It shows some emission bands from carbonaceous dust, which is not common in less evolved stars. So probably this one is an early stage of protoplanetary nebula. We were not able to detect the secondary because we didn't have enough good spectra. It's a 12th magnitude star compared to red rectangle, which is a 9th magnitude star. But this comparison gives us hope that we can find the secondary in the future, and that's again another manifestation of about the same observational behavior. And here another sort of manifestation of that same phenomenon. I showed that slide at the previous conference. So this is a 10th magnitude star, which was not studied in the optical. before we turned to it. And it was known as an iris source, detected in the infrared. This is a region of oxygen triplet at 7772 to 7775. And sometimes an absorption feature develops here. There is no sign of any changes in photometry. So just plain same brightness. But a similar feature appears near many other lines, like hydrogen lines, H alpha, H beta, some helium lines, but it's fainter in fainter lines. So here is what this feature looks like in the H beta line profile. But one of our colleagues, Daniela Korchakova from Prague, found that in the infrared, the lines are split. So this is the spectrum of the star, this is spectrum of Vega, because it's very similar to Vega in the optical, but these lines are split. And the explanation is Zeeman effect. So there should be a very big magnetic field. And this magnetic field is not comparable to those found in BE stars or Herbig stars. In BE or Herbigs, they are in the range of a few Gauss, maybe 100 Gauss, up to, well, there are some very young stars which show, just single stars which show magnetic field with the strength of about 2 kilogauss. But this has 7 kilogauss. And this star is not supposed to be a young star. There is no star-forming region around it. There is no cluster where it formed. So it's alone, but there was a sign that it might have been ejected from a cluster, but we don't see any nearby cluster. Probably already dispersed cluster. So it's more or less evolved, maybe at the end of the main sequence. But typically magnetic stars, there are magnetic stars with stronger fields. By the end of the main sequence, the magnetic field disappears. So it gets to 500 Gauss, 1 kilogauss at most. But this one still shows about 7 kilogauss, and it turns out that it's probably periodically changes. And when we studied this feature, which appears and disappears, so this is kind of a quiet state, this is when that feature appears. And it turns out that it's regular with a period of about 36 days. So Danielle published a paper. I decided not to be part of that team because I disagreed with her a little bit. And we continued observing that star. And you see that it's a periodical variation with this period. So we need to figure out what that period is. Maybe rotation of the star, or maybe it's due to binarity. And here is the equivalent of the Chalfa line, which also follows that period. Not very strict, but the periodicity, the appearance of that absorption feature comes into view regularly, as I can predict now. And the final, final object is a 13th magnitude star with very odd hydrogen and iron line profiles, typically in BE stars and many other stars which are surrounded by disks. The widths of the components are about the same of the double peaked feature. But here the blue peak is fainter, which is typical in FS Canis Majoris object, but it's much broader than this one. And you look at some other lines, like sodium line, in the spectrum. It was compared to Ida Carinae at some point in the late 70s. But Ida Carinae is much hotter. So this one is also a B-type star, but not as hot as Ida Carinae. Anyway, it's a distant one. If you look at the map, at the sky, there is no any kind of nebula there. But also, before, because the observations were not at high resolution, not high signal to noise, people didn't see any structure near the continuum. And with the help of observations from CFHT, just 2 spectra, one of which was accumulated for 10 hours of observing, we recognized some absorption lines, which are similar to those in the only known binary that at that time it was the only known, now there are a few, of the same kind of object. So we have some cool star, because those neutral metal lines cannot be created in a hot star atmosphere. So we know that there is a hot component which produces emission line spectrum. Nothing from the hot companion in terms of absorption lines, and no helium there. So we, using spectral energy distribution, we disentangled the hot component with this temperature, and cool component with this temperature, and this is the contribution of the cool component. And this way we were able to fit the spectral energy distribution in the optical range. And this is the infrared excess, so there is a lot of dust around it. Then we looked at the Brussels group calculations of the evolution, and we found kind of a rough model for this object. So this is what the hot star, where the hot star is on the characteristic diagram. This is where the cool star, and this is the first system in this group which has an ongoing, which seems to have an ongoing mass transfer. This is how the masses of the components change. So the letters B and E stand for the beginning and ending of the mass transfer due to Rochelot overflow. It's supposed to be a very tight binary, and probably just surrounded by a common envelope. So we study more and more objects. We discover more and more effects, which are in a number of cases unusual. So we see that even our group, which is defined by the range of luminosities, the range of masses of the primary components, can be caught at different stages of the evolution of such mass transfer binaries. And it makes this project very exciting and interesting. So, summarizing everything, there are some kind of general conclusions which you can read here. I won't do that. But for me, studying any kind of binaries, whether they interact or not interact, very exciting, and it helps me to attract students even at our university where there's no astronomy problem. So thank you for your attention.
You said for the B bracket is one class is compact BNs.
Yeah, that's the original definition from the discoverers.
How is compact defined spatially?
Yeah, so you don't see planetary nebulae around them, but it's a spectroscopic definition. The spectra is similar to those of some planetary nebulae, especially with high excitation lines like O3, forbidden lines.
This trigger, I thought about that, so it triggers my second question.
Mm-hmm.
Maybe it's just too cool, but are there any protoplanetaries?
Yeah, yeah. At that time, protoplanetaries were not defined.
Okay.
Yeah.
I'm ahead of schedule.
I think, yeah, they were defined back in the 80s, but the discovery was done in the 70s.
Nice talk, and I would certainly discuss with you later. But just a few questions. First, you mentioned several times that the evolutionary tracks you were using were from the Brussels group.
Yeah.
But you didn't do it for the first case. It was also Brussels evolutionary tracks?
For which one?
I think it was MWC 78.
Yeah, it was
also
yeah.
Brussels. Okay. Then I have a question. For the second IRAS object, with the Z-man, yeah, with the Z-man effect, it's actually very funny, because if you look at the H alpha equivalent with evolution we have, It's basically exactly what we have with our magnetic O-type star. It's very, very similar, which doesn't prevent them to be binaries also, but it's not seen in the H alpha. But it's beautiful. It's exactly the same beautiful thing.
Okay. I'm interested in your stuff.
Yeah, and I had a question. Well, I can also propose you to do X-ray observations because with the magnetic objects, with that type of thing, it may be very interesting to try that. The magnetosphere would be huge, and so I think it would be worth a try, even if the star is quite late. Mm-hmm. Anyway.
but it's not in any X-ray catalogs, as far as I know.
Sure, you have to ask. Deadline is soon.
Yeah, but you may think that in surveys it would show up, but maybe not.
Not necessarily.
It's a close one.
For doing our survey of magnetic OB stars, we had to do quite a lot of dedicated observations. Anyway, I was wondering, considering what you said about this star, if it could fit the scenario of Fabian Schneider, meaning that it would be the product of a merger.
Yeah, that was one of the hypotheses which we considered, but
I'm not a big fan of that scenario for other reasons, but it seems to me that
it's definitely possible.
Yeah, it looks like a promising thing, at least for this one.
But it's low mass.
Yeah.
I don't know. Yeah, it may be a possibility again, but
you could have ejection during this merger, so it could move.
Yeah. That's definitely.
Okay.
Right.
Because then I have
Dr. Scorpii, of course.
Yeah.
Some questions. The peristaltic passage is gone, but are the requirement of further data?
Yeah.
Yeah, but because you show a picture where was a suggestion of the peristal time. Could you see? No, it was.
Well, we still need to observe it, and it's easy. First magnitude star, just 10 minutes, and you get a good spectrum. All our spectra have signal to noise of about 300 at least.
No, my question was, could you determine the peristal time from this from our contributed spectral material?
Yeah, we will combine everything.
The question was, are now spectra required or not? Because the peristal time is
yeah, but we still, so this is a week ago, the last point.
Yeah.
So it's still recovering from that radial velocity change. So it's.
So it means the spectra are required.
Yeah, it will be good. And by the way, I didn't mention that. So the spectral line profile in the previous periastron and now is very different.
Yeah.
So the line was weaker than it is here, and you see that central peak.
Mm-hmm.
The tilt angle is about 45 degrees or 50 degrees. So we should have seen the double peak structure, but it's veiled. It's covered by some radiation from an additional part, which may not be in the plane of the disk. Mm-hmm. Which is the same, by the way, in gamma cos and in pi Aquarii when it was in its full glory with larger and disk and more material. Yes.
It means there could be influences of the mass of the companion.
Well, when they come together at periastron, the secondary companion goes into the disk. And then we just need some theoretical calculations.
The influence of the line profile from periastron to the next level is always different.
Yeah.
Yeah?
Yeah, the emission line.
The emission line, yeah.
For the absorption line, we're still looking for the contribution of the secondary companion, which is about 1.5 magnitude fainter from the interferometric data than the primary structure.
Yeah.
It's your talk time.
Yeah, but I still have one question for you.
Yeah.
For the B bracket E star, there was one where you shoot spectra and the lines, the emission line was, oh yeah, go back. Yeah, why are those lines so asymmetric?
Well, we think that this is a contribution from a jet.
No, but you look at the other ones, the iron ones, they are really, those small ones, they are really like...
They're similar. So it's a similar pattern.
They have these broad wings to the blue,
Yes.
and not scattering wings to the red.
Yeah.
Yeah, and if the hydrogen lines were fainter, then I think you would see the same thing. So
You
it's,
mean it's a blend?
Hmm?
You mean it's a blend?
No, this is one line, that complicated profile. And I believe, I see some support in modeling like beta Lyrae, for example, that it may be a contribution from a jet. So there is mass transfer and part of it goes as a jet perpendicular to the disk. Again, that's just kind of a vague initial suggestion. But it's a unique star. So there are a number of other stars with such a rich emission line spectrum, but those line profiles, there is no match to this one. And all other pieces of our information kind of point towards an ongoing mass transfer.
Before you show the diagram where you had, I think 2.6 cycles a day and 1 cycle a day, 1.6,
Yeah.
and the comment was it could be daily aliasing.
Yeah.
Yeah, that's what I said.
I fully agree on that, it's
Yeah.
1 cycle a day apart. But you say you also see something of line splitting in, this one.
Yeah.
Any chance on SPB star, and you see line profile variations? Because they're huge.
Doesn't look like. So this is secondary companion, this is primary companion.
So
Yeah, they seem to be normal
you were
stars.
talking about you suggested a third component because of additional splitting.
Well, again,
And
it's
could
just a
that
wild
be-
idea. Yeah. It's a wild idea. Maybe, you
And
know.
my question was, could that be oscillations? Because
Well, maybe. Again, it was studied before, but those people did not suggest any deviations from normality for those stars. So we will see that when the analysis is done.
Because some time ago we studied an SPB star from Pride photometry and high resolution spectroscopy. We knew there was a triple system and we had problems to find the orbit because the oscillations were so brutally. So
Maybe absolutely. So need to apply for Bright. It's 4.5 magnitude star. All right, I'm done.
thank you.
Thank you.